Good morning, boys and girls, and welcome back to day 3 of finding volumes of solids. Today we are no longer revolving around the x or y axis or a vertical horizontal line. Today we're going to find volumes of solids with given cross sections. All right. So problems look kind of like this: find the volume of the solid whose base is bounded by the circle x squared plus y squared equals 4, with the indicated cross section taken perpendicular to the x-axis. Right? And so our first cross section our cross sections are going to be squares. All right. So what we got going on here, if we draw ourselves a little picture, we have our circle, right? X squared plus y squared equals 4 is a circle, radius of 2. So it looks something kind of like that. Oh man, I do a way better circle on the board. Let's give it one more go here. That's not bad. That'll work. Okay, so we have our circle. And we are taking cross sections that are squares. All right. So, like, if you just imagine if I were to take a square, and whatever that, chord of the circle is there, that becomes the length of our squared. And it's going to kind of stick up out of the circle. The circle is the base, and that's going to kind of stick up like that. So the smaller, the smaller the chord, the smaller the square. As you get to the ends, as you get towards the middle, the bigger the diameter then, the bigger your square is going to be. All right? This is one of those things, again, you want to try to draw yourself a picture, but it's a little hard to really see what's going on. But again, our cross sections are going to be these squares that will eventually form a solid. All right? I have another website that helps us kind of visualize a little bit. Let's see if this helps. All right, so kind of a little bit weird, but we have our circle base here, all right? And then again, what this is going to show us is we're going to have our squares, wrong direction, have our squares, and so you can see that the diameter or the chord of the square, or of the chord of the circle becomes the length of the square. And so that the longer that chord gets, and again, we're just going to do a bunch of squares, that's going to create a solid. So our solid would kind of end up looking like this. Hope this will help us visualize it a little bit, but you're going to just take a bunch of squares, an infinite number of squares basically, and we're going to make it look like that. All right, let me show you another look at this. All right, so here's another look at this shape. We got our squares already all kind of built in here. We are just going to spin it around. But you can see that when you do this, that's why those lines were there. You get this kind of, interesting looking shape here. And then again, if we were to do it an infinite number of times, I'll give you one more view of what this shape would look like. All right, so if you did it an infinite number of times, you would have your bunch of squares and they would create a solid shape like this. And so you would get something that would kind of look like this. On the very ends of the circle, when we're at like 2 and negative 2 on the x-axis, it'd be that little tiny kind of the V part. And then as it gets bigger, that's when you're at the Y part at the very top with the most orange. All right? So we're going to try to find the volume of this solid right here. All right? Okay, so whenever you're finding the volume of a solid with a given cross-section, you are always going to use this general formula here. It is the integral from start to finish of the area of the shape. So whatever our shape is, again, in this case, we're going to do squares, area of the shape, and then dx or dy depending on what it's perpendicular to. So for our example here, these are all going to be perpendicular to the x-axis, so we're going to say dx. Okay, and we're going to integrate with respect to x. If we wanted shapes that instead were perpendicular to the y-axis, and so maybe my square went this way instead, and popped out. If it went that way, perpendicular to the y-axis, then I'd say dy. All right? But that's the general formula that we want to use. All right, so now let's set this up. All right, so to find the area of a square, it is, base times height or side times side. So area of our shape is side squared, so we're going to integrate side squared. We'd want to start, again, our circle starts at negative 2 and goes to 2. And then the height of our triangle, or of our square, well, this is the y value of the coordinate right there, right? So I need, the side of the square is twice that amount then, because I got, half above and half below. So our side of the square would be 2y. Squared dx. Does that make sense? Y is the amount we go up from the x-axis. Does that make sense? Like, you guys can answer me. Y is the amount we go up from the x-axis, so that is the y coordinate. And now, to be just a little bit more specific, because again, I want to integrate with respect to x, I would come back up here and I would solve our x squared plus y squared equals 4. I would solve that for y. Y squared equals 4 minus x squared, or y equals, again, technically plus or minus the square root of 4 minus x squared. But we're just playing with the top half, and we're going to double it since it's symmetric. And so we are going to do the integral from negative 2 to 2. I could square this and make that 4y squared. I'm going to pull that 4 out to the front. And then y is the square root of 4 minus x squared dx. So that is going to be the setup that we want to use to find the volume of this shape. All right. And now again, you could square this. When you square it, it's nice. It gets rid of the radical. I'll let you go and evaluate that on your own. But when you do evaluate it, you should get 128 over 3. I don't know if my video gets in the way for you guys. I can kind of see it here, so I'm trying to draw around it. So, but 128 over 3. Maybe we'll come to this side. 128 over 3. Maybe that's better. That would be the volume once you evaluate that integral. All right. Let's set up another one now. Similar idea. We're going to deal with the same circle. Okay, x squared plus y squared equals 4. Except for now, we are going to do cross sections that are triangles. Okay, triangles. Equilateral triangles, even better. Okay, so same idea. We're going to find the volume of the solid whose base is bounded by that same circle and whose cross sections are taken perpendicular to the x-axis. Again, that's important. That tells me what to integrate with respect to. But these are now going to be equilateral triangles. All right. So now instead of making a square, when it pops out towards the front, it's going to be a triangle. So we're going to get a bunch of little triangles like this. This helps you view it a little bit. That last one was kind of bad, but it'll look like that. Again, let's go back. I've got this set up on our friendly website. This one I think is kind of cool to look at. All right, the same idea as last time. We are going to add triangles, and I don't believe these ones are equilateral. These are maybe more isosceles, but it's enough to give us the idea, right? We're going to just add a bunch of triangles to create a solid, right? So it kind of looks something a little bit like that. Okay, if we're going to take those triangles and kind of spin this around so we can look at it, it's going to look kind of like this in 3 dimensions. Interesting. And now on to the best part. If you were to look at your full shape once it's all filled in and everything, this is what it's going to look like. All right. This one I think gets extra neat if you speed it up a little bit even. It just kind of gets fun to look at. Look at that thing twist. But this is the volume. This is the shape of the volume that we are trying to find. Okay, what is the volume of this shape? You see our little vertex is all going down the middle of it. All right, now let's go do it. Wow, after looking at that cool illustration, just makes me realize how bad my drawings really are. All right, so we said to do this, when you're trying to find the volume of a given cross-section, always, always, always integral area of the shape. In this case, we're doing a triangle, so 1/2 base times height, and again, dx, because we're doing it with respect to the x-axis. And I guess we could still even add, going from -2 to 2 still, are going to be our limits. All right, now you might remember from geometry, I think there is a formula. I'm pretty sure there's a formula. I know there is, I just can't never remember it. For the area of an equilateral triangle, but I always got to go and I just always derive it again. But if you wanted to go look up that formula and memorize it, you could use it. It'll work similar to what I'm about to do right here. But if I needed the area for a triangle, again, it's base times height. With an equilateral triangle, I don't know what this is here, right? It's just like some side. With an equilateral triangle, I do know the angles are 60 though, and the height cuts a right angle. So this creates me some 30, 60, 90s, right? 30, 60, 90s. And so if I call this, this half piece here, the side, then using my ratio of a 30, 60, 90, I know that this is 2 times whatever that side is, and then this becomes side root 3, right? Side root 3, 2 side, x root 3, 2x. Those are the ratios of a 30, 60, 90, back from geometry. So, if I know this side, then I can find the area of my triangle. In this case here, the side, again, is like that half right there. So the side in this case is equal to the y value, right? So I'm going to go from -2 to 2. I can pull the 1/2 out in front if I wanted to, right? I'm going to leave it here for right now. You'll see why. But 1/2. So the base then is 2 sides, right? 2 s's or 2 y's. And the height then is side root 3 or y root 3 dx. And now again, now that I've kind of worked that out, I now can go back. We solved for y before. Y is equal to the square root of 4 minus x squared. And now I could plug in for y. And so this is -2 to 2. 1/2 times 2 is just 1. So it just becomes 1y. So square root of 4 minus x squared times another square root of 4 minus x squared times root 3 dx. And again, you'll notice conveniently our square roots are going to kill each other off, which is going to make us happy and easy to do. I can even pull out this root 3 to the very front so that I don't have to deal with it. And really then we can just integrate, -2 to 2 with the root 3 in front of 4 minus x squared dx. So you can see that these simplify down to something that is, really not bad at all. All right. One other trick I want to show you here that I could do. I could also, instead of going from -2 to 2, because that might be tricky, plugging in -2 is not fun, right? You can double it since it's symmetric and go from 0 to 2 of 4 minus x squared. And that way when you plug in 0, it's going to make your life happier. So that's another trick you can use. Anyway, when you get your answer, you should get 32 root 3 over 3 as the volume of this solid. All right, here we go. One more. All right, the same idea in this case, same base, the circle, but now we're going to do with cross sections perpendicular to the x-axis that are semicircles. So it would look kind of like this. I don't have a fancy illustration for this one here, but hopefully you can kind of get an idea. Basically, this is going to start to look like a hemisphere in this case. All right, so the way I want to do this, though, is integral area of the shape. So my shape is a semicircle, so 1/2 pi r squared. Again, we're going to go from -2 to 2 and dx because we're perpendicular to the x-axis. Our radius in this case is just that y value, right? Our r is equal to the y. So now I'm going to pull out the 1/2 and the pi, integral -2 to 2. My y value is the radius, so that again was the square root of 4 minus x squared dx. And again, just kind of doing some simplifying stuff, I could double this and go from 0 to 2. So if I double the 1/2, I get 1, and I can go from 0 to 2. And if I square that, again, I'm back to my 4 minus x squared dx. And when I do this, you should get 16 pi over 3. All right, I lied. I think I said one more after the last problem. We got one more problem now. You'll see these ones, when you get the hang of them, they're really not that bad. It's just integral area of the shape. All right, here's one more that's not on a circle. Okay, so now we want to find the volume of a solid whose base is bound by the graphs of y equals x plus 1, the line, and y equals x squared minus 1, the parabola. Cross sections are squares and are taken perpendicular to the x-axis. So draw a picture. Here is our parabola and our line. And now, again, they're perpendicular to the x-axis, but we're going to do squares inside this area, so something kind of like that. All right? So we're going to integrate the area of the shape dx. So in this case, again, side squared dx. And now I just need to find out where the intersect so I know where to start and stop my integral. So when I set these equations equal to each other and solve that system, we get x equals 2 and -1. Now to figure out what the length of the squares, or what the side of the squared is, it's just top curve minus bottom curve. Don't forget to square your side, simplify, and evaluate, but you should get 81 over 10. All right, that's it, boys and girls. Have a great day, and I'll see you again soon.